Chapter 1, Introduction to Simulation, Part 3. So after having the basic definition simulation model, let's see what are the types of simulations. Uh, we can have static or dynamic simulation. So the static simulation is called Monte Carlo simulation as well. So when you hear a Monte Carlo simulation, it's a static simulation. So what's the difference between these two? The Monte Carlo or static simulation is about operation at a particular time, but the dynamic simulation is over a period of time. So in the Monte Carlo, we don't have a period of time. It's it's just one shot, and we are interested on the outcome of that one shot. For example, a game outcome. So let's say we are interested in the outcome of the games in a league, not the events happening during the game, right? So in that case, we are not interested in the events during the game, and we're interested just the outcome of the games. So, and we are going to have a simulation model to predict the result or the outcome of the games. So in that case, we call this as a Monte Carlo simulation or static simulation. But if we're interested to the process, over time, to the operation over time, or the events that are happening over time, then that will be a dynamic a simulation model, like simulating a bank from time 9 a.m. to 4 p.m. to see what's happening in the bank during this period of time. Okay, so this is called a dynamic simulation model. Another type of simulation could be deterministic versus stochastic. Okay, so if the inputs of the simulation are known, so we call this as a deterministic model. But if they are random, we call that as a stochastic simulation model, like interest return from savings. So yeah, if you have a saving account, you are considering the saving investment. So, and based on the interest rate, the interest return will be obtained exactly, right? So we call them as deterministic. But return from shares in stock market, they are not deterministic, so it's stochastic, right? Or for example, patients of a doctor's office coming by appointment, or so yeah, if the patients have appointment, so we know that what time which customer will arrive the doctor's office, right? So it's a deterministic model. But in walk-in clinics, there is no certainty, and customer will arrive in random fashion, right? So it's a stochastic simulation. Okay, and another type or another category for the simulation models is a discrete versus continuous. uh, as I said before, if the system's state is changing just in discrete point of times, so that's a discrete simulation model. But if it's changing continuously over time, so it's a continuous simulation model. Like number of people in a queue is a discrete system versus gas in a pipeline. That will be a continuous, right? So as you see here in these two graphs, discrete state and continuous time. So time is continuous, but change in the system state is happening in discrete point of times. So as here, the system state is at this level, it remains constant for a while. Then at this time, it changes to this number, right? To this level. And again, it remains constant for a while, and then it drops to another level at this time again, remains constant, increase, remains constant, and increase and decrease. Okay, but here, as you see here in this graph, the time is continuous, same as the previous one. Time is continuous in both cases, but the only thing varies here is change in the system state. In the discrete system, the change in the system state is happening in discrete point of times, but in the continuous system, the change in the system state is continuously happening over time. Like the gas, let's say the gas pressure in a pipeline, or the position of airplane, or the speed, and so on. So these are actually in the category of continuous systems, right? Now, based on the definitions, we can categorize the simulation models in this slide, and we'll see in what kind of simulation model we are going to focus in our course. So the system model could be deterministic or stochastic, right? And so in this course, we are going to work on stochastic systems, not deterministic ones. So we'll focus on a stochastic system. So a stochastic simulation model could be static or dynamic. So if it's static, I mean Monte Carlo simulation, it's called Monte Carlo simulation. So there's no period of time, and we are just interested on the outcome, and it's happening by a random fashion. I mean, the outcome is not known certainly, so it's stochastic, but there is no track of time here. So because of that, we call this as a static simulation model or Monte Carlo simulation. And in dynamic, stochastic dynamic simulation, it could be again continuous or discrete. And again, in this course, we are going to consider just the discrete simulation models. So because of all these ones, we have a term here, discrete event simulation, DES, discrete event simulation. And the models that we are going to consider in this course is, our discrete event simulation models. Okay, so in this course, we'll have stochastic systems, we will have static or dynamic stochastic systems. So yeah, we will consider also Monte Carlo simulation in our course. And in dynamic stochastic systems, we will just consider the discrete ones, not the continuous ones. Okay, so because of that, we call the models as discrete event simulation models. Okay. So in discrete event simulation models, the system is modeled in terms of state variables, and state variables are changing only in a discrete set of points in time. Let's have an example here. We have an airport here, and as you see here, the system's state will be changed by occurring the events, right? For example, here we have at time 8, we have an arrival. Okay, so by happening this event at time 8, we have a new arrival to the airport. So the system state will be changed. I mean, the number of arrivals will be increased by 1 by happening of this event. Again, from this point up to this point, there will be no change. I mean, the system state will be constant. And at this time, let me show by at this time, we will have a new event, which is landing that airplane. So again, by happening this event, the system state will be changed. I mean, the number of landed airplanes will be increased by 1 by this event. And again, from this point up to this point, there will be no change in the system state, right? Because we have no event over this uh, period, right? So at this time, again, we have an event which is a departure. So departure is going to be occurred at time 9:15. So by happening of this event, we will have a change in system state. The number of departed airplanes will be increased by 1 by occurring this event. Again, no change in from this point up to this point because we have another arrival at time 9:30. So yeah, so again at that time at 9:30 the system state will be changed. So as you see here, the system state is changing discretely, just in discrete set of times over continuous time, and because of that we call this as a discrete event simulation model. Okay, so as you see here, we can define the events. So here we have arrival event, we have landing event, we have departure event. So by having these events and the time of occurrence of these events, we will have a future event list, and by having that future event list, we can actually simulate the operation or the process of these kind of systems, right? So this is how a discrete event simulation model works. Okay. So in discrete event simulation model, the operation of the system is represented as a chronological sequence of events. Okay, so yeah, here time can be continuous or discrete, but the change in the system is happening in discrete point of times. Okay, system evolves by jumping from one time epoch to the next. For example, yeah, in the real system, there will be one event here and another event here and another event here and so on. Okay, so we know that in the system state, in the real system, the change in the system is happening just in these points. For example, let's say if let's say it's for the customer's arrival. Okay, so we have one arrival here, another arrival here, another one, and there will be no arrival of new customers during this time period up to this time. Okay, that's what happening in the actual system. But in the simulation model, we don't need to wait for this long time to have the new customer. We just jump over time. Yeah, we at this time we have clock in the simulation model, and we know what's the time here, and we have the event. Then we jump from this time to this time. We won't wait for this long to have the new event. We just jump from time t to t, let's say prime here, or to let's say t1, t2, and t3 and t4. Okay, and we just jump from one time to another time in order to have the new event and then process the impact of that event in the system. That's it. So because of that, we can simulate the operation of an actual system, let's say for a month. Yeah, I mean a monthly operation of a system just in a few seconds in the simulation model. So this is why we say that having a model, a simulation model, is cheaper and faster than experimenting on actual system. Yeah, in actual system, if you want to experiment physically in the actual system, you need to wait for a month to see what's the result, right? But in simulation, you can simulate the system just in a few seconds, right? So because we jump over times, we know that there will be no change, there will be nothing happening during this time. Okay, so because of that, we just jump from time to time based on the time occurrence of the events. Okay. Okay, so the key elements here that we have in a simulation, in a discrete event simulation model, are state variables. Usually they are discrete. Clock, it is continuous but jumping time to time, right? And event list, which is a sequence of events based on their occurrence time, and also random numbers. So you may say, what's random number here? You will see that we actually process the simulation, I mean the discrete simulation, by generating random numbers. You'll see very soon that how we use random numbers to simulate the operation of a system in a simulation model. Okay. So here we will have an example, and we call this as simulation by hand. So we are going to do the simulation, I mean discrete event simulation by hand here to see how a simulation software works. Okay, so here we are going to manually track the state variables or statistical accumulators, and in order to do it by hand, we will consider the given interval and service times, right? So yeah, here we assume that we are given the interval and service times. So we keep track of feature event list, or FEL, and we lurch clock from one event to next. I mean jumping from time to time of one event to the next event. Okay. So this example is about a simple processing machine or system. So here we have the parts coming to the system, part number 1, 2, 3, and so on. So here we have the arrival times. You are given the arrival times here, so we know at what time each part will arrive to our system. And here we have the inter-arrival times, okay, and also the service time. So part number 1 arrives at time 0, and the next part should arrive after 1.73, let's say, minutes or seconds or hours. It depends what's the time unit here, but let's say minutes. Okay, and we know that and here we are given that the service time for part number 1 is 2.90 minutes. Okay, so the second part will arrive at time 1.73, and the next part, I mean part number 3, should arrive after 1.35, so it will be 3.08. Okay, and the service time for part number 2 is 1.76 minutes or hours. Okay, so yeah, here we are given this interval time and also service time, but in a simulation model we will generate these values by statistical distributions. Yeah, we have to fit the statistical distribution for inter-arrival time, considering the historical data that we have in the actual system, and also we need to fit the statistical distribution for service time, again considering the historical data that we have from the actual system, and then based on those two statistical distributions we will generate random numbers, and these are, let's say, generated random numbers from the appropriate distributions, and based on that we can say we know that at what time what kind of event is going to be happen. Okay, and here we're going to simulate the system for 20 minutes, and we will stop simulating the system at time 20. So time 20 will be the stop time. Okay, so here we will define the FEL, feature event list, or event calendar, and as you know that we need to order the events in the FEL based on the occurrence time. So the structure of the event list or FEL would be this. We'll have 3 elements in the FEL: entity number, event time, and event type. Okay, so entity number, it could be the customers or part numbers, and event time, the occurrence time of that event, and event type. It could be arrival or it could be departure. So arrival of new customer, arrival of new part, departure of the current customer or part, and also it could be the end event. I mean the end of simulation, which will be happen at time 20. Okay, and here we need also to define state variables. State variables are going to describe the current status of the system, right? So here we define these two state variables. Server status at time t, we show this by bt, and it can take a value of 1 or 0. 1 for busy and 0 for being idle. Okay, and the number of customers or parts in the queue at time t, we show this by qt. Okay, so the number of customers or parts in the line at time t, we show this by qt. Okay, other variables like times of arrival of each customer in the queue can be defined as well, but we just consider the first two ones, server status at time t and number of customers in queue at time t. Okay, so now we are going to see how we can simulate the system by hand, and it will be in the next part of this chapter. Okay, thank you.